We're starting a 2-day lesson today, and actually most of the week we're going to be looking at this same topic. It all has to do with something called concurrent lines, and concurrent lines are 3 or more lines that meet at one point. Okay, so like it's just 3 lines that are coming together. So maybe we have one line there, another line there, and then a third one. So those would be concurrent lines, just 3 lines that come together and meet at one point. So in my picture, that point right there is where they meet. That point is called the point of concurrency, which makes sense. Where concurrent lines meet, we call that the point of concurrency. So, like I said, this whole week and for this 2-day kind of lesson that's going on, it's all about different kinds of concurrent lines. So, we're going to use our contractor to kind of like draw a picture of this first set of concurrent lines. So, it says here, construct the perpendicular bisectors of 2 sides of the triangle below. So that's the fish thing, if you kind of remember that with our contractor stuff. Okay, so if you remember how to do that, I'm just going to take 2 sides, it doesn't matter, so I'm going to start with this side here. And I'm going to do like the fish thing. So I put the brass circle at one end point, and I pick one of these holes that goes over halfway. Looks like I should be good with 50, and I'm going to make a big arc. And then I'm going to swing the brass circle around to the other side of the triangle, the other end point, and make an arc at 50 over here. And I should be looking at the fish thing then, which I am, so that looks good. Where your fish came together, you draw the perpendicular bisector by connecting those 2 points. So it's going to look something like that. Okay, so there's one perpendicular bisector. They told me to do that for 2 different sides, so I'm going to pick this side right here. And it does not matter which 2 sides you choose. So I put the brass circle at one end point. I'm going to go for 50 again. I'm going to swing the brass circle around to the other end point of that side and do 50. And mine was real close. Where they cross, you want to connect your fish. And notice I'm using pen to like draw the perpendicular bisector. And I'm just doing that so it stands out a little bit more. Okay. Now, where those 2 perpendicular bisectors met, and realistically, you guys, if I would have done the 3rd side here, that perpendicular bisector would have met at that exact same point. So if that would have been the case, and I could do it, I'm not going to because I don't need to, all the perpendicular bisectors, they meet at one point, and that's right here on this picture. Now, again, if we would have drawn all 3, they're concurrent lines, these perpendicular bisectors. Where they meet, that point has a name. Yes, it's a point of concurrency. It's where the lines come together. But in this specific case, it's called the circumcenter. So you're going to notice that there's a lot of vocab that shows up in this lesson and in tomorrow's lesson. The circumcenter is the point of concurrency, so I'm going to fill it in down here. The circumcenter is the point of concurrency. It's where the lines come together of the perpendicular bisectors. Okay, so we constructed the perpendicular bisectors where they came together. That's called the circumcenter. And yes, that is something that you will have to memorize, but we'll get to that point, no worries. Now, there's a theorem. So this little thing here is a theorem which can be proven, and you kind of just take the picture's word for it. The circumcenter, this point, is the same distance from the angles of a triangle. Okay, so the circumcenter right here is the same distance from all three of the angles of a triangle. And I'll kind of show you an easy way to remember that in a second. Now, there's also this third thing that we want to note down here. And you can actually draw a circle around this center. This center is the center of the circle that's drawn around the triangle. Okay, so we can kind of draw that, and let's fill in at the bottom here first. This circle, and you can kind of see the picture here, we're going to draw that on our little diagram up top. This circle that's around the triangle is called a circumscribed circle. And right here is the circumcenter on their picture. You can see like the perpendicular bisector here, here, and here. All three of those are coming together to meet at the circumcenter. So the circumcenter is the center of the circumscribed circle, the circle around the triangle. So we're going to kind of write that in there. A circle is circumscribed, we're going to say about a polygon when the vertices of the polygon are on the circle. Okay, so you kind of look at the triangle. Vertices just means the angles. So like every angle of my triangle here is on the circle. Okay, so the circle around a triangle or a shape is called a circumscribed circle. We can draw that on our picture, and here's how we would do that. So you'd put the brass circle on the circumcenter, and the circle should just touch all three of the angles. So you kind of have to like play around with it. I just matched it up with 1 point. Let's see, it looks like kind of 51 is going right over that vertice there. So I'd kind of swing it around. Yep, and 51 just touches that angle. And, ooh, it's a little off here, so mine's not perfect. Maybe we should try a smaller number. Maybe 50 looks a little bit closer. It's not going to be perfect, and I'm not going to grade you on it being perfect as long as it's pretty close. So 50 kind of looks a little bit better from my little viewpoint here. So what you would do is put your pen or pencil in 50, and slowly you would just take that all the way around. Okay, so as you can see, mine was not perfect. I missed this point right here. I shouldn't have done that. I should go back and kind of like fix it, but it's probably just because my fish thing, I used pen, so sometimes when you connect the fish, it's not totally accurate because it's thicker. But you get the idea. Each point should lie on your circle, and this one I kind of have to like fib a little bit. That's okay. So if you guys think about it, and that's the circumcenter where the perpendicular bisectors meet, it's the center of the circle that's around the triangle. Now, if you think about it, and here's how I kind of remember this theorem thing down here, that it's the same distance from the angles. The angles are on the circle. So like if you think about the radius, that's kind of how I think of it. Radius is from the center to the circle. It's like that's a radius, that's a radius, that's a radius. The radius is the same distance no matter where you draw it. So that distance and that distance and that distance from the center to the angles, it's all the same. Okay, so if you kind of think the radius of the circle, it might help you remember that the circumcenter is the same distance from the angles. Okay, so that's a lot of information, but that's one point of concurrency. We've got another point of concurrency that we're talking about on the back. So instead of doing perpendicular bisectors, we're going to use our contractor to do angle bisectors. Okay, so if you remember how to do that, it's kind of been a while since we've done bisectors with our contractor. You need to pick, and it just says, ooh, this should say angles here. Let's fix that. I'm just going to bisect 2 of the angles. And the third one should go right through it, so we only need to do 2. So I'm going to pick this angle at the bottom left. And to bisect it, you put the brass circle on the vertex of the angle. And I usually stick with 30. You just make an arc so it hits the angle in both places. Okay, where it hits, so I know I'm going to draw something like this that's cutting that angle of the triangle in half. So you put the brass circle at one intersection point, and I just pick 30 and I make a mark like floating out in space here. And then I bring the brass circle to the other intersection point and make the exact same arc. Now, where your little arcs met, you connect that to the vertice, and that's your angle bisector. So I'm going to use pen again so that way it sticks out. Okay, there's one angle bisector. I'm going to do another one, so maybe I'll just do this top angle. So I'm going to put the brass circle on the vertex, and I'm going to make an arc at 30. And I've got two intersection points here. And I'm going to put the brass circle at one intersection point and make a mark at 30. Ooh, it might not be a bad idea to use a different color here because all these marks are coming together, but I think I can decipher it. Make another mark at 30. Okay, where these two marks met is right here. This looks gross, but I'm going to connect this angle through that intersection point. And there's my second angle bisector. Now, the reason they said 3, and I'm going to go ahead and do this third one just to kind of like show you that you only have to do 2 because they should all intersect at the same point. So it doesn't matter that you don't do the third one. Because watch, when I connect this, it's going to go right through where those first two met. So don't waste your time doing all 3, just do 2. And where they meet, right there, let's do another color. So these are concurrent lines, 3 angle bisectors coming together. This point of concurrency where the angle bisectors meet, this one, it's not called the circumcenter. This one's called the incenter. Okay, so it's kind of the same idea, except this time it's the point of concurrency of the angle bisectors, not the perpendicular bisectors. Now, it's like the exact opposite of the circumcenter, and this one's a theorem too that we could prove. Now, the circumcenter was the same distance from the angles. The incenter is the opposite. It's the same distance from the sides of the triangle. And I'll show you kind of a way to remember that in just a second. There's a circle that's related to the incenter. The incenter, and if I look at my picture here, this is the incenter. All the angles are being cut in half, and where they meet, that's the incenter. So they're trying to show you that. The incenter is the center of the inscribed circle. And you can kind of see the picture here. The circle is not around the triangle anymore. It's inside or inscribed. Kind of easy to remember, inside, inscribed. Okay, so center of the inscribed circle. Okay, down here it says a circle is inscribed in a polygon, so it's inside a shape, if the sides of the shape are tangent to the circle. Now this is weird, we've never seen that word before. Tangent just means that it only touches in one place. Okay, so what they mean by that, and we're going to draw our inscribed circle up here on our top picture. But what they mean is like the circle just barely grazes each side. So like it only touches each side in one exact place. That's what tangent means here. So let's draw this. You put the brass circle to draw this inscribed circle. You put the brass circle on the incenter. And instead of matching up which hole goes right over the vertices, you want to match up which hole is, like, when you draw the circle, just barely going to touch all 3 sides of the triangle. And I really hope mine is a little bit more accurate than my last one. So maybe focus on like 25 is looking pretty close. Like it doesn't go outside of the circle at all. And you just want to barely touch. And I'm kind of thinking 26 for mine is a little bit more accurate. Okay, so again, maybe go all the way around before you draw it. You just want it to barely graze all three sides. And I'm going for it. 26 looks good. So hold down your brass circle real tight. And just go all the way around with 26. So much better. So it should just touch each side in one place. That's the inscribed circle. Now, to remember this theorem, guys, and you will have to remember it, I use the radius of the circle again. So radius goes from the center to a point, center to a point, center to a point. The radius is the same no matter where you draw it, and the radius really, it goes from the center to the side of the circle, or to the side of the triangle, center to the side, center to the side. So this center is the exact same distance from all three sides of the triangle. Not the angles, doesn't help. Exact same distance from the sides.